Greetings, class. Welcome to this premium academic explainer. Go ahead and get settled, grab your notebooks, and get ready because we're about to master the fundamental physical rules that literally govern our universe. Consider this for a second. Particles in the Large Hadron Collider are pushed to approach the absolute speed of light. To do that, we need immense, unbelievably powerful superconducting magnets just to slightly change their path. The sheer effort required to alter their motion is staggering. Today we will study dynamics, momentum, and Newton's laws. Here's our roadmap for today. We're going to start with linear momentum fundamentals, then work our way through the first, second, and third laws, including conservation and gravity, before wrapping it all up with a high-yield summary. It's a packed agenda, so let's get right to it. Okay, let's dive into this with Section 1, Linear Momentum Fundamentals, or Defining Mass in Motion. To really make sense of motion, we first need a concept that combines how much stuff is moving with exactly how fast it's moving. And that brings us to linear momentum. By definition, a particle's linear momentum, which we represent with a lowercase p, is just the product of its mass, m, and its velocity, v. Mathematically, it's as simple as p equals m times v. Now, because velocity has a specific direction, momentum is intrinsically a vector quantity. Its magnitude and its direction are identical to that of the velocity. We measure this in kilogram meters per second, or when we're doing impulse calculations, the Newton second. Think back to our Large Hadron Collider hook. Because those subatomic particles are traveling at such mind-bending velocities, their momentum becomes absolutely immense. And that massive momentum dictates the exact powerful resultant force required to change their path. Moving into Section 2, the first law and conservation. Because once we've defined momentum, we really need to see how it behaves when a system is completely undisturbed. Newton's first law strictly states, every object continues in a state of rest or uniform velocity unless acted upon by a resultant force. This right here is the absolute baseline of systemic stability. When you look at this first law through the lens of momentum, a pretty profound physical rule emerges. Think about it. If an object maintains uniform velocity, its momentum is unchanged. If it's at rest, its momentum stays at zero. Basically, momentum remains completely constant unless an external resultant force acts on it. And this gives us the principle of conservation of momentum. In a closed system, total momentum remains absolutely constant. No exceptions. And this brilliantly illustrates how we take theoretical physics and apply it to the real world. Picture two water drops in a cloud, right? Just about to collide midair. Pre-collision, they each have their own individual momentum, defined by P equals mv. Upon interaction, they collide and coalesce into one single drop. Post-collision, assuming there's no major air resistance acting as an outside force, the total mass of this new drop multiplied by its new velocity will exactly equal the sum of their original momenta. The math balances out perfectly.
Listed are the main insights for the heading discussed. Note them specifically since they are highly relevant for exams.
Let's shift gears a bit. Section 3, the second law, and the quantitative link. We're moving from qualitative ideas to applying resultant forces mathematically. The first law tells us what happens when forces are absent, but we need to rigorously define what happens when a resultant force is actually applied. Newton's second law provides that quantitative link. It states that the resultant force acting on an object is strictly proportional to the rate of change of its momentum. Let's derive one of the most famous equations in all of science. By defining the Newton so that our constant of proportionality is exactly 1, the formal definition is force equals the change in momentum over time, or F equals delta P over delta T. Now, if the mass remains constant, any change in momentum is due entirely to a change in velocity. And since a change in velocity over time is just acceleration, this law simplifies beautifully into F equals ma. You just have to love how physicists take the chaotic reality of the universe and condense it down to a simple memory trick. Force makes acceleration. From that equation, we can precisely define the unit of force. 1 Newton is the exact force required to accelerate a 1 kilogram mass at a rate of 1 meter per second squared. And you'll actually prove this in a classic A-level lab investigation. You take a low-friction trolley on a track, making sure to maintain a constant system mass. As you increase the pulling force using hanging weights, you measure the resulting acceleration with light gates. When you plot force against acceleration, you get a perfectly linear graph, where the gradient represents that constant mass. It's a really elegant way to validate F equals ma right on the lab bench.
These are the vital facts linked to this section. Study them thoroughly as they are vital for examination point of view.
All right, section 4, gravity, mass, and weight. We're taking F equals ma out of the lab and applying it to forces near Earth's surface. All objects near Earth's surface experience a constant acceleration of freefall. This leads us right to the scientific definition of weight. Unlike mass, weight is a vector force representing gravity acting on an object, directed straight down towards the center of the Earth. By just swapping in g for acceleration in our previous formula, we get W equals mg. So the crucial point is distinguishing mass from weight. Mass is just the quantity of matter, but weight is the actual force. For example, a 1 kilogram mass has a weight of 9.81 newtons here on Earth. In modern aerospace engineering, this distinction is absolutely vital. As a satellite moves further out into space, its mass stays perfectly constant, but its weight drops because the local gravitational pull is decreasing. Engineers have to continuously calculate this changing weight to figure out the precise thrust needed for orbital maneuvers. Let's move to and see how this builds into the equipment we use every day in the lab. A Newton balance measures weight directly using the extension of a calibrated spring reacting to a downward force. A top pan balance feels downward pressure, sure, but it's internally calibrated to read out mass. On the flip side, a lever or beam balance actually compares an unknown mass to standard masses. It relies entirely on equilibrium. Because gravity is pulling equally on both sides of the pivot, reaching equilibrium guarantees the masses are equal, completely regardless of local gravity. Moving on to section 5, the third law and contact. This deals with complex interactions, and honestly, it's often the most misunderstood of the three. We need to analyze what actually happens when multiple bodies interact. Newton's third law states, whenever one object exerts a force on another, the second object exerts an equal and opposite force on the first. The beautiful symmetry of the universe is embedded right in this law. No, what's really interesting about this slide is how easily these forces get confused. Think of a simple book resting on a table. The Earth pulls the book down, that's weight, and the table pushes the book up, that's normal contact force. But these are just balanced forces creating equilibrium because they act on the same body, the book. A true third law pair always acts on different bodies. So the third law pair here is the table pushes the book up and the book pushes the table down. That upward push from the table is the normal contact force. It arises from physical touch and acts perpendicularly to the surface. Modern biomechanics actually relies entirely on mastering this. Take prosthetic design, for example. The normal contact force between a prosthetic socket and a patient's skin has to be meticulously managed. If the pressure is uneven, the equal and opposite third law reaction from the skin can cause severe tissue damage. Medical engineers are quite literally using Newton's laws every single day to ensure patient safety.
These are the vital facts linked to this section. Study them thoroughly as they are vital for examination point of view.
Let's lock all of this in with a rapid-fire, high-yield summary. Remember your core formulas. Linear momentum, P equals mv, dictates mass in motion. Newton's first law guarantees momentum conservation in a closed system. The second law is our quantitative powerhouse, F equals m. Gravitational force gives us weight, where W equals mg, heavily dependent on local gravity. And finally, the third law ensures that forces always exist in equal and opposite pairs acting on different bodies. I want to leave you with this final lingering thought. Considering the careful distribution of third law, equal and opposite forces needed to protect tissue in biomechanics, how might engineers apply these exact same contact force principles to design safer crumple zones in modern aerospace vehicles? Think deeply on that physics application and keep exploring.
Relevant keywords for this topic are shown on the screen, grouped by different examination boards. These terms need special attention during study as they are critical and should not be ignored under any condition. Along with this, past paper analysis is given for every board and type of paper. Be sure to review this thoroughly as it will help improve your preparation significantly. Also focus on understanding the meaning and application of each keyword instead of memorizing them individually. Regular practice using these terms in past paper will increase your accuracy and exam success.
Please subscribe our channel to get more educational videos. Thank you.